For this video, I'm going to walk you through calculating KEQ and also being able to calculate the concentrations at equilibrium as well using ice tables here. So right now, if you know all of the concentrations or all of the pressures at equilibrium in a problem, that's key. In order to plug into KEQ, you must know all the concentrations or pressures at equilibrium, not just initial concentrations or pressures. You must know all the concentrations and pressures at equilibrium. If you know them all at equilibrium, just plug in to your KEQ expression and then solve the problem. It's that simple. As long as you know all the values at equilibrium, you can plug them into KEQ and solve for KEQ. So if you look at this very first example here, it says the reaction below takes place in a sealed flask. Determine the value of the equilibrium constant with the following concentrations at equilibrium. So they're telling you all of these concentrations are at equilibrium. So they gave you all the concentrations for everything in this reaction. All right, so if you want to calculate the equilibrium constant, the KEQ, first of all, you need to write the KEQ. So we do products over reactants. They're all gases, so they're all going to be included here. Remember, the coefficients are going to be the exponents here for a particular substance. So when we write that, we get our products over reactants. Pay attention to those coefficients. And now we just plug in the values they gave us because we know all of the concentrations at equilibrium. All right, because we know all the concentrations at equilibrium, we can just plug into our KEQ expression. When you do the math, you get a KEQ of being 0.16. All right, so it's that simple to solve a KEQ. If you need to find the KEQ, plug in your concentrations or pressures at equilibrium and just do the math. But obviously, you need to write the KEQ correctly, and you need to make sure that you are actually using the concentrations or pressures at equilibrium. Now we're going to look at something here called the reaction quotient, or Q. Basically, Q will tell you about your system when you are not at equilibrium. All right, so if you have kind of concentrations here for your reactants and products and you haven't reached equilibrium yet, Q will tell you kind of which way the reaction is going to shift in order to reach equilibrium. And it's pretty simple. You just take your concentration or pressure values that you have at any point here in a reaction, and you just plug them into your KEQ expression. All right, so it's not like you have to learn how to write a new expression or anything. You just take your KEQ expression, plug in the values you have, and solve for it to get Q. The reason why it's not KEQ and it has to be Q is because, remember, you can only plug in equilibrium concentrations into KEQ. All right, but you're using the same expression here in order to get Q. All right, and as I said, this is going to be able to tell you which way the reaction will go to establish equilibrium. So again, if you have your generic equation here and you write the KEQ expression for that, you know how to write a KEQ expression, products over reactants, paying attention to the coefficients here and making them the exponents. But this time, it's just Q equals that. All right, because basically these concentrations are not at equilibrium. That's why it's not a KEQ. But this is very helpful because it will tell you at any point in a reaction which way the reaction is going to shift or which way the reaction is going to go in order to reach that equilibrium state. So if you have some concentrations here or pressures that aren't at equilibrium and you're not sure which way the reaction needs to go to kind of finish up in order to get to equilibrium, this is very important to figure that out. In order to figure out which way the reaction will go to reach equilibrium, you just have to compare Q to your KEQ value for that particular reaction. If Q is equal to K, so when you plug in your concentrations, all right, if you find out that Q is equal to K, well, that means you're at equilibrium. Essentially, you plugged in equilibrium concentrations into your KEQ expression, and that's why they came out to be equal. If you calculate Q and Q is greater than K, then that means your products are greater and the reaction is going to need to shift left. Okay? Essentially, you have too many products forming or too many products compared to what you should have at equilibrium. So the reaction needs to reverse and go to the left or go to the reactant side. If you have Q being less than K, essentially what that means is that you have too many reactants present. You need to use up those reactants in order to get to equilibrium. So the reaction is going to need to shift to the right. Essentially, the forward reaction is going to need to take place. You're going to need to form more products. So this is very important. You need to compare Q to K in order to figure out which way the reaction will go in order to reach that equilibrium state. I like to use this little trick to help me remember which way the reaction is going to go. Use the little alligator trick here. So essentially, we know we have to compare Q to K. All right, so we think of the greater than or less sign as being like an alligator. So if Q is greater than K, all right, the alligator mouth is going to go to the left. All right, you can see it's kind of going to eat the Q there. All right, so that indicates that the reaction needs to form reactants or shift to the left here in order to reach equilibrium. And then obviously, if Q is less than K, the alligator is going to the right here. It's going to eat the K. So you need to form products where the reaction is going to shift to the right side here. Okay, so I find this little trick to actually help me remember which way the reaction is going to go when I compare Q to K. Remember, this is going to tell us which way the reaction is going to shift in order to reach that equilibrium state. Let's look at an example here involving this idea of Q. So it says for the reaction below, KQ equals 50. Predict which way the reaction will shift to achieve equilibrium if the current concentrations are as follows. So the first thing to take note of here is they're just giving you concentrations. They did not tell you that these concentrations are at equilibrium, right? So you don't have equilibrium concentrations. You can't just plug them in to KEQ. We want to know which way the reaction is going to shift in order to achieve equilibrium given these concentrations that aren't at equilibrium, all right? So in order to figure out which way it's going to shift, I have to do Q. But remember, you're essentially writing a KEQ here. So we know Q would be equal to products over reactants raised to the power here of their coefficients. All right, so it's going to be the concentration here of HI squared all over concentration of H2 times the concentration of I2. All right, remember, these are all included here in your equilibrium constant expression, or in this case, your Q expression, because they're all gases, all right, products over reactants. So now I can plug in here. Remember, these are not the concentrations at equilibrium. They're just concentrations of your current state. That's why we're using Q here. So when I plug them in, I have 0.02 for the concentration of the HI, and that's going to be squared all over the concentration here of the H2, which is 0.01, times concentration of the I2, which is 0.03. Okay, so now when you just plug and chug here and solve for Q, you get 1.3. So remember, you have to compare Q to K. So if I compare Q here to K, if you look at the problem, they told me the K EQ was 50. So if you want to write them here just to help, and we know the Q is 1.3. So comparing Q to K, I can see that Q is less than K. So if you used a little alligator trick here, the reaction is going to go toward the right side, right? So you're going to form products, all right? And this proves that you understand why the reaction is going to shift to the right. You have to kind of usually prove this here with work and obviously get the right value for Q and then compare it to K to know that it shifts right. So you might be given a problem like this where you have to figure out which way the reaction is going to shift, or this could be used in these equilibrium problems, as you will see. We already looked at how to calculate KEQ if you know all the concentrations at equilibrium. You just plug into KEQ and solve. Well, what if the concentration of the species at equilibrium are not all known? Okay, so now we have to kind of approach this differently. If you don't know all the concentrations at equilibrium, you can't just plug into KEQ and solve. So if you know at least one of those concentrations and the balanced equation here, we can use stoic and mole ratios to determine the concentration at equilibrium by using something called ice tables here. All right, so this is kind of the version of the problem where we know one of the concentrations at equilibrium. All right, that's key. We know one of the concentrations, at least one of the concentrations at equilibrium, but we don't know all of them. So you would write down all your givens in the balanced equation. You determine the change in concentration using the mole ratio, and then you'll set up your ice table. I'll show you what this looks like, but ice stands for the initial, the change, and then your concentration at equilibrium. And the sign of the change does matter, all right? And we'll look at this as we go through. So right now I'm kind of just giving you a general idea. And then once you do have all your concentrations at equilibrium, you can plug into KEQ and solve. All right, so I like to call these versions of the equilibrium problems logic and math versions. So basically, you have at least one of the concentrations at equilibrium. So you kind of have to use logic and math here in order to figure out the other concentrations at equilibrium so you can plug in and solve. All right, so we're going to look at how you would do problems like this. Before we go any further here, we need to know what an ice table looks like and how it is set up. So this is the basic gist here of an ice table, and you don't have to necessarily, set it up like a perfect table with all the lines and stuff. You'll see when we start going through problems how we just kind of make this kind of resemble a table here. But the basic gist is the balanced equation goes kind of at the top of the table, and then you have your I, C, and E going down the left side. Your initial um, row here is going to include the initial concentrations of each of the species or your substances from your problem. The change would be the change that's taking place in the reaction according to X, and then equilibrium would be your concentration at equilibrium. Remember, if you're trying to plug into KEQ, you need to plug in your concentrations at equilibrium in order to do that. All right, so this is the basic setup here of an ice table, and you'll see how we use this and kind of a little bit more about what we plug in here as we go forward. Let's jump in and look at an example here. This is telling us a closed system contains a certain amount of H2 and I2 and is allowed to reach equilibrium. It says the concentration of HI at equilibrium is 0.00187 molar. Okay, and we want to calculate the KEQ for this reaction below. The first thing you need to realize here is, okay, I'm finding KEQ, but I don't have all the concentrations at equilibrium. If I had all the concentrations at equilibrium, I would just plug into KEQ and solve. I don't. But I do have at least one of the concentrations at equilibrium. That's important here because that's what's going to make this a logic and math version of one of these equilibrium problems. You know at least one concentration equilibrium. They told me the concentration of the HI at equilibrium. So I set up my ice table right away as soon as I know this is going to be an equilibrium problem here and I don't have all the concentrations at equilibrium. So you can see your initial change in equilibrium there on the left. I put the substances in the reaction here at the top, and I did include the amounts. The amounts are important here, okay? So the first thing we're going to do is we're just going to fill in what we were given in the problem. Based on the information I have from the problem, I know the initial concentrations of the H2 and the I2 here. All right, be very careful on the wording. These are not the concentrations at equilibrium. These are the initial concentrations of the H2 and the I2. But I also know the concentration of the HI at equilibrium. So that's why I wrote that one down here in the equilibrium row. Because I know one of the concentrations at equilibrium, that's what makes this a logic and math version of the problem. So now we need to fill in the rest of the table here using logic and math. The first thing that I'm going to fill in is the initial concentration of the HI. Basically, if these two substances were present initially, these are my reactants. I don't have any products here. All right. So I have 0 HI initially. All right. Because I know the concentration of the HI at equilibrium, I can actually figure out what the change in concentration here would be. So again, you can see how I'm kind of using logic and math here to fill out the rest of the table. This has got to be 0 because there are no products initially. And now that I know this was 0 and I know the concentration of the HI at equilibrium, I can determine the change here. So based on the fact that I had none initially and at equilibrium I ended up with that much, I must have gained 0.00187 molar here. So that would be my change for the HI. Notice it's positive because the product is forming. All right. I'm starting with reactants, I'm forming products, so the product is going to be positive. Your reactants are going to be used up, so the reactants would be negative for the change here. All right, so it's very important that you understand what's forming and what's being used up here. But do you see how, because we knew initially this was 0 and we knew its concentration at equilibrium, we were able to determine the change here for the HI. But now we need to go and determine the change for our reactants. We can use the change in HI to figure out the change of the reactants here. If the product or the HI here gained that much, we know that the reactants needed to lose that much, but because of the stoich here, because there's twice as much HI forming, they're not going to lose that exact amount. They're going to lose half of that amount. So if you notice, there's going to be a negative change here because the reactants are being lost, but they're going to be 0.00187 divided by 2. All right, you do have to pay attention to the mole ratios here. If it was 1-to-1, it would just be the 0.00187 being lost for each of them. But because there's twice as much product compared to the reactants, they have to be half as much for their change. All right, so that's something you got to pay attention to. Again, I told you this was kind of a logic and math version of an equilibrium problem, so you do have to think a little bit here. All right, so now we know the change for each of the reactants. So I just did the math here. I did the 0.00187 divided by 2 for each of these, and that's what I got. All right, so now to determine the concentration for each of these at equilibrium, you just need to do the math. You have an initial value for each. They're changing or they're losing this much, all right? So you do the subtracting to get the equilibrium value. Same thing here. This is how much I2 you started with. It's changing or losing that much, so you can determine the equilibrium concentration here now of the I2 by just subtracting the initial minus the change. When you do that, now you get the values here at equilibrium for the H2 and the I2. So if you noticed, we used logic and math here in order to fill out the rest of our table. And we were able to do this because we knew at least one of the concentrations at equilibrium. In order to do a logic and math version of these equilibrium problems, you have to know at least one of the concentrations at equilibrium. So now that we have all of the concentrations here at equilibrium, now we can just take those values and plug into our KEQ. Remember, we need the concentrations at equilibrium in order to plug into KEQ. When you write your KEQ for this reaction, remember products over reactants, pay attention to your coefficients, making them the exponents here for a particular substance. So we wrote our KEQ, and when you're doing these equilibrium problems, get used to writing out your KEQ and showing it. All right, you have to show what the KEQ would be, and then now we can just plug in our equilibrium values here into our KEQ expression. That's very important. You need to use the equilibrium values in the KEQ expression, not the initial values or the change. So I plug in those values. When I do the math, I get a KEQ equal to 50. All right, so this is just showing you an equilibrium version of the problem here where you had at least one of the concentrations at equilibrium. Then you could use logic and math along with your ICE table in order to find the other concentrations at equilibrium. Let's look at another example here. This one says initially a vessel with SO3 gas has a partial pressure of 0.500 atms. At equilibrium, the partial pressure of the SO3 is 0.200 atms, and we want to calculate Kp. All right. First thing I notice is I don't know all the concentrations, or in this case, the pressures at equilibrium, so I can't just plug into Kp and solve. But I do know the partial pressure here of at least one of the substances at equilibrium. I know the partial pressure of the SO3 at equilibrium. So it's going to be a logic and math version of the problem. So I'm going to need to write my ice table. I'm going to use the reaction that I have written here in order to kind of set up my ice table. So I'm just going to set up my ice table right along with this reaction. I have my I, my C, and my E, my initial, my change, and my equilibrium here. All these substances are gases, so they're all going to participate here. Based on the information I know from the problem, they told me the initial pressure here of the SO3 is 0.500 atms. And they told me the equilibrium partial pressure of the SO3 is 0.200 atms. All right, so that's the only information I got here. But notice I know at least one of the pressures at equilibrium, so it's going to be a logic and math version of the problem. So I have to fill in what I know here now. I know that because the SO3 is my reactant, initially I don't have any of my products. They didn't tell me we have any products forming. There are no products here. But because I know the initial and the equilibrium here for the SO3, I can determine the change. Obviously, this is a reactant. It's going to be used up to form the products. So the change for the SO3 is going to be negative. Based on the fact that I started at 0.500 and at equilibrium I'm at 0.200, I must have changed by 0.300 atms. All right. Now, for the change for each of my products here, I know the products in this case are going to form. So I know they're both going to be positive. I do have to pay attention to the mole ratio here. If you notice, for every 2 of the SO3 that react, there are going to be 2 of the SO2 that form, so the same amount. But there's only going to be 1 of the O2. So I need to take that into account here as I do my change. So the ratio for the SO3 and the SO2 are exactly the same. So if I lost that much SO3, I'm going to gain that exact same amount for the SO2. But for the O2, I don't have the same ratio. Essentially, I have half as much forming. So I'm going to gain 0.300 divided by 2. All right, so that would be 0.150 atms. So you do need to pay attention to the stoich here when you're doing your change. All right, obviously, again, the sign matters. The reactant's going to be used up. In this case, the products are going to form. So now when I do the math here, plug in my equilibrium constant, or excuse me, my equilibrium pressures for the SO2, I have 0.300 atms at equilibrium because obviously 0 plus 0.3 is going to be 0.3. And then for the O2, it's just going to be the 0.150 atms for the pressure of that one at equilibrium. So now I know all the pressures at equilibrium. Now I can plug in and solve here for the Kp. But I obviously have to write the Kp expression first. I know it's going to be Kp is going to be equal to the pressure of the SO2 squared times the pressure here of the O2. Again, products over reactants, all over the pressure of the SO3, and that's going to be squared as well here. So now you just need to plug in your pressures here at equilibrium. All right, so from the equilibrium row in your ice table, you get 0.300 squared times 0.150 all over your 0.200 squared. And when you do your math here and you solve this, you should get 0.338. All right, so that would be the Kp for this problem. Remember, the reason why we had to use this logic and math version was because we knew at least one of the concentrations, or in this case, pressure, at equilibrium. So it's going to be using the ice table here with logic and math. We've already looked at what you do if you have all the concentrations at equilibrium. You just plug them into KEQ and solve. We've already looked at what you do if you have one of the concentrations at equilibrium. You basically use logic and math. But what if you don't know any of the concentrations at equilibrium? Okay, so you don't know any of the concentrations at equilibrium. You have to determine all those concentrations using ice tables and X here. You might even need to use the quadratic equation for some of these questions in order to solve. So just a refresher here, the quadratic equation, you might need to know this if you don't know it already. Negative b plus or minus the square root of b squared minus 4ac all over 2a. You have to basically get the problem into this form in order to plug in the a, b, and c into the quadratic equation. So you need your x squared first, then your x term, and then your number with no x, and set it equal to 0, and then you could plug into the quadratic equation. All right, so this is how you would do problems if you don't know any of the concentrations at equilibrium. You're going to have to do ice table with x. We are going to jump right in and look at an example. So this problem says the value of KEQ for a reaction below is 50. We want to know the concentration at equilibrium for all species if the initial concentrations are as follows. All right, so notice we are not given any of the concentrations at equilibrium. So we can't use logic and math here because we don't know any of the concentrations at equilibrium. So we have to set up our ice table. So you can see here, I set up the ice table for the reaction, and now we're ready to start plugging in what we know. Based on the problem here, I know the initial concentrations of the H2 and the I2 here. All right, so if I have an initial concentration of the H2 and I2, I can assume that the initial concentration here of the product is 0. Essentially, I don't have any of the product to start. All right, so I know my initial, and pretty much that's it. So now I have to figure out the change for each in terms of X. Let's look at the change for the reactants first. So if you notice here, I don't know what the change obviously is for the hydrogen, but I know it's going to be negative because the reactants are going to be used up to form your products here. So it's going to be some negative X essentially. And notice the coefficient is just 1, so I'm just losing some amount here of X, essentially 1X. The ratio from H2 to I2 is exactly the same. So it's also going to be negative because it's a reactant. It's going to be decreasing. It's going to decrease by some value of X here. All right. So now I need to look at what the change would be for the product here. The product is forming, so it's going to be positive, and it's going to be forming some value of X, but because of the mole ratio here, it's going to be forming 2X. All right, so essentially each of these is losing a certain amount, but the product is going to be gaining twice that amount because of the balanced equation here. All right, so now that I have all of my changes for the reactants and products, I can now do my initial, all right, minus the change for each of the reactants, and my initial plus the change for the product, and plug that into my ice table. So when you do that, the initial minus the change here for the H2 is 1 minus X molar. That would be the concentration at equilibrium for the H2. The I2 would be 2 minus X molar, and then the concentration at equilibrium for the HI would just be 2X molar, because 0 plus 2X is 2X. So now I have my values for each of these concentrations at equilibrium, okay? So now we can plug in to KEQ and solve. Remember, your goal here is to get those concentrations at equilibrium in order to plug in to KEQ. I have to write my KEQ expression first. Remember, you do need to show your KEQ expression. Get used to showing it. So we do products over reactants. Pay attention that they're all gases. Don't forget that the coefficients become the exponents here in your KEQ expression. So this would be my KEQ for that reaction. Plug in what you know. In this case, we knew the KEQ. They told us that the KEQ was 50. Plug in your concentrations at equilibrium for each of the substances. All right. And now that you have everything plugged in, you're going to need to simplify here and start rearranging these terms. So you're probably going to have to do FOIL down here, the first two terms, the outer terms, the inner terms, and the last two terms. And then obviously you're going to need to simplify and rearrange this. So you can see I kind of simplified this a little bit, and then when I continue my math, you can see how eventually I get to a point where I have this set up as 46x squared minus 150x plus 100. Essentially, I have it in the correct form now that I can use the quadratic equation here. This would be my A term, this would be my B term, and this would be my C term. So now you're going to need to be able to do the math here and plug this into the quadratic equation to solve for x. I strongly urge you to make sure that you can actually do this math here, get to this point, and that you can plug this in to the quadratic equation to get the answers that I get on the next slide. This is something that you need to be able to do. You need to be able to do the math here. Remember that when you're doing the quadratic equation, you have negative b plus or minus. So essentially, you always get two answers here from the quadratic equation. But one of your answers always gets rejected. All right, so you're going to calculate the quadratic equation. You're going to get your two answers. Then you have to see which answer doesn't make sense. So for this, these are the two answers I got when I did the quadratic equation. Again, I strongly urge you to do the math, make sure you can get to this point. All right. So when x is 2.33, notice when I would plug that in for my equilibrium values, I get negative numbers here. 1 minus 2.33 gives me a negative value for the concentration at equilibrium. That doesn't make sense. That can't happen. So this answer gets rejected. All right. The only answer of the two that makes sense is the 0.934. All right. So that's the value here of x. You wouldn't just circle x and say, oh, I'm done. No, that's not what we wanted to know. We wanted to know the concentration of each of these substances at equilibrium. So right now, what you did was you just found x, or you found the change using the quadratic. You have to kind of finish the problem here and now determine those values at equilibrium. So remember, you're always going to get two answers here when you have to use quadratic. One of them is going to be rejected because it doesn't make sense. The last thing I need to do is take that value of x and plug in to each of the equilibriums here to get my concentration for each substance at equilibrium. We try to be careful here and watch sig figs and such. So I get the concentration of the H2, the I2, and the HI at equilibrium. Now, you could take these values and plug them back into your KQ expression and see if what you get is close to the value of KEQ they gave you in the problem if you want to check your work. It's not required, but it's something you could do if you were unsure here. When I plug those equilibrium values back into my KEQ expression, I do get 47.1, which was very close to the original value of 50 that they told me. It's probably off just a little bit because of sig figs and such. So that means I probably did the problem correct. So remember, this would be how you do one of these equilibrium problems when you don't know any of the concentrations at equilibrium. You have to use x here in your problem, and you have to solve the problem for x in order to do this. Let's look at a little summary here of the different types of equilibrium problems that you might see. All right, these summary slides are very important because they're trying to basically get you to focus on what you're going to see here, the different types, and how to kind of go about solving them. So if you know all the concentrations at equilibrium, all right, every concentration at equilibrium, just plug that in to KEQ and you solve for KEQ. That's the simplest version here. If you know one of the concentrations at equilibrium, you're going to need to use an ice table, and you're going to need to do what we call logic and math in order to figure out the other concentrations. Remember, there's no x here. You're using logic and math. If you don't know any of the concentrations at equilibrium, that's when you're going to need to use an ice table with x. That's what we just saw. All right. There's one other version here which we didn't explicitly do yet. Basically, if you don't know any of the concentrations at equilibrium and none of the initial concentrations are zero, okay? Essentially, you don't know which way the reaction is going to go because you don't have any initial concentrations being zero. So you have to do Q first to figure out which way the reaction is going to shift, all right? That tells you, uh, whether the reactants are going to be positive and gaining or whether reactants are going to be negative and losing, okay? So it's going to basically be the exact same type here as, using X and an ice table if you don't know any of the concentrations at equilibrium. But because none of the initial concentrations are zero, you have to solve for Q first, compare that to K, figure out which way the reaction is going to go so you know the sign here of your change. But then it's going to be, plugging into the ice table and solving for X. So these are the different versions here that you need to look out for. You need to be able to look at a problem and say, okay, this is going to be, which of these types in order to solve it. A couple of things here that you want to be on the lookout for. First, always set up your ice table with the balanced equation. All right, make sure you're paying attention to the stoich here, and obviously you need to pay attention to the sign of the change, whether something's going to be losing or gaining, all right, negative or positive. Uh, Always write the equilibrium expression, no solids here. All right, if you have a solid or a liquid in your reaction, they just wouldn't be a part of your ice table. Essentially, where that substance is in your ice table, you just put a line through, right? Because the solids or liquids are not part of equilibrium. They don't participate in your ice table either. When we're doing concentration, it needs to be in moles per liter. All right, so sometimes you might see problems here where you're given moles. All right, well, that's not concentration. You need to be in moles per liter. Um, if you're solving one of these versions of the problems for X and you get a perfect square, you can take the square root of both sides in order to not have to use the quadratic. It makes your math a little bit easier here. But if that's not a possibility, you can't take the square root of both sides, then you're going to have to use the quadratic equation, and you need to know that quadratic equation. And obviously, check your work, be careful here. There's a lot of places you can mess up. You really need to think your way through these problems, but these are things that I definitely have found you need to be on the lookout for and make sure you don't fall for any of these traps. So let's do some examples here. This first one says for the reaction below, the KEQ at 200 degrees Celsius is 4.2. What is the concentration at equilibrium for all species if initially there are 0.25 moles of H2 and CO2 in a 5-liter closed container? All right, so the first thing I'm kind of looking for immediately is, do I know any of the concentrations at equilibrium? And from what the problem is asking me and telling me, uh, I have to find the concentration at equilibrium for all species. So I don't know any of the concentrations at equilibrium. I know this is going to be an ice table with X, all right? I can see here that I have the initial moles here of the H2 and the CO2, all right? So that means the H2O and the CO are going to be zero initially, all right? So this is just going to be a basic, I don't know any of the concentrations at equilibrium, so I'm going to have to use ice table with X. The first thing I got to be careful of is that they gave me the moles of H2 and CO2. I cannot use moles. I have to use concentration here. So they did give me the liters, so I can quickly find the concentration. That's something you want to watch out for. You can't put moles into your ice table. So I have 0.25 moles of each of these, and it's in a 5-liter container. So when I do the math here, I get 0.050 molar for the concentration of the H2 and the concentration of the CO2 here initially based on what they told me in the problem. So now I'm going to set up my ice table here. All right. So when I plug in my values, I know that there's 0.050 molar initially of the H2, 0.050 molar initially of the CO2. All right, so you can't use moles. You must be in molarity if we're using concentration. Initially, I don't have any H2O or CO. Because I don't have any of the products, I know which way the reaction is going to go. I'm going to use up the reactants forming the product. So as the reactants are used up, that change is going to be negative, and the products are going to be formed, so their change is going to be positive here. I said we don't know any of the concentrations at equilibrium, so we're going to have to use X. It's all one-to-one here, so this makes it really easy. The reactants are going to lose some value of X, and then the products are each going to gain some value of X because we're forming products. So now when I write my concentrations at equilibrium, I get 0.050 minus X molar. Same thing for this one, 0.050 minus X molar. This would be X molar at equilibrium, and this one would be X molar at equilibrium. So now I have all the concentrations here at equilibrium. I need to plug in to KEQ. So I need to write my KEQ expression, right? Products over reactants. So we're going to have H2O, concentration of H2O times the concentration of CO. Again, they're all one-to-one. They're all gases, so they're all going to be in my equilibrium constant expression, all over the concentration of H2 times the concentration of CO2. So I wrote my equilibrium expression. Now I'm ready to plug in what I know. They told me the KEQ was 4.2, and that's going to be equal to the concentration of H2O times the concentration of CO, which are both X. So that's just going to be X squared here, all over the concentration of H2 times the concentration of CO2. They're both the same. So essentially it's going to be 0.050 minus X squared, okay? Because you'd be multiplying the two together, which are the same. So if you didn't notice here, this is a perfect square on the right side. I can take the square root of both sides and make the math a lot easier. I don't have to do quadratic here. Right? I have x squared on top. The bottom is 0.050 minus x squared. That's a perfect square. So it makes the math a lot easier. So I take the square root of both sides here. And you do need to do the math to solve for x. I would make sure that you can do this in order to get to that point here, because you have to be able to solve this for x. When you do the square root, I will say you get 2.049390153 equal to x over the 0.050 minus x. Okay, so you still need to keep going there in order to solve for x, but when you do the math, and again, I would make sure you can do this, you should get x equals 0.034 molar. All right, so that's your value of x. That's not the concentration of each of these at equilibrium. You have to go back and plug into your ice table in order to get those concentrations. All right, so obviously, in order to do the concentration of your H2 and CO2, you're going to have to do the 0.050 minus the 0.034, all right, in order to get both of their concentrations, which would be the 0.016 molar when you do that math. All right, so I'm just going to list all the concentrations here. You do the subtraction for the H2 and the CO2. So the concentration of H2 and the concentration here of the CO2 are both going to be 0.016 molar. And then the concentration of the H2O and the concentration of your CO are both X, so they're just going to both be 0.034 molar. So now I know the concentration of all of the substances here at equilibrium, which is what I wanted to do. All right, so I didn't know any of the concentrations at equilibrium. I had to use ice table with X, but this problem I had to be careful, make sure that I'm using molarity. Let's look at one more example here. This one says for the reaction below, the KEQ is 1.15 times 10 to the second at a certain temperature. If we have 2.50 molar H2, same for F2, and 0.500 molar of HF present in a flask, determine the concentration at equilibrium for all. So the first thing I'm trying to do here is figure out, okay, which version of the problem is this going to be? It looks like I'm solving for the concentration at equilibrium for all of these. So I don't know any of the concentrations at equilibrium. I'm going to need to use the ice table with X, all right? But the problem here is that none of these substances initially are zero. If you notice, they gave me the concentration of the H2 initially, concentration of the F2 initially, and the concentration of the HF. So I don't have any of the initial concentrations being zero. That means I have to do Q first in order to figure out which way the reaction is going to proceed in order to reach equilibrium here. All right, so I'm going to write my Q expression. Q will be equal to concentration of HF squared, products, over reactants, concentration of H2 times the concentration of F2. Okay, so I have to write my Q expression. Remember, it's just your KQ expression, but we're using Q because we're not plugging in values that are at equilibrium. So when I plug in those values here, I should get 0.500 squared, all right, because that's the initial that they gave me. Remember, this is kind of like a snapshot of your reaction. Here's the concentrations, all right? You're taking those concentrations, plugging them into Q to figure out which way the reaction is going to shift here. So that's going to be all over the 2.50 times 2.50 here. They're both 2.50. So when I plug and chug that, the value I get for Q is 0.04. All right. So when I compare Q to K here, so Q compared to K, K is 1.15 times 10 to the second, which is the same thing as 115. So obviously Q is going to be less than K. And remember, you can't just guess. You have to go through, solve for Q, and show the comparison. Based on the alligator trick here, the alligator is going to the right. All right, so this reaction is going to shift to the right. So that means we are going to form product in this case. You can't just assume that the product is going to form. All right, comparing Q to K tells us that the reaction is going to form the products here. So now when I set up my ice table, I know that the products are going to be positive and the reactants are going to be negative. I had to do Q initially here because none of my initial concentrations were zero. So I needed to do Q to figure out which way the reaction was going to shift. So now I can set up my ice table here. All right, initial concentrations we were given in the problem for these. So we know it's 2.50 molar, 2.50 molar, and 0.500 molar for the HF. Change, we just figured out that the reaction is going to go to the right here. So I know the reactants are going to be used up. They're going to be negative, and the product's going to be formed. So it's going to be positive here. Okay, so if we look at the stoich here, the reactants are going to lose some amount of X, and the product is going to gain 2X because there's 2 HF for every one of each of the reactants. So when I write my equilibrium concentrations, it's going to be 2.50 minus X molar, 2.50 minus X molar, and then 0.500 plus 2x molar for the concentration at equilibrium for the HF here. All right, so I already wrote my KEQ expression in terms of Q, so I don't need to rewrite the KEQ expression. I just need to plug in what I know here. They told me KEQ was 115, and that's going to be equal to my 0.500 plus 2x here, and that's going to be squared according to the KEQ expression, all over the 2.50 minus x, and that's going to be squared because each of the reactants is 2.50 minus x for their concentration at equilibrium. So again, you get a perfect square here. You don't have to do the quadratic, so you can take the square root of both sides. All right, it makes your math a little bit easier, but you still are going to need to be able to do that math make sure you can do it. I strongly urge you not to just, smile and nod and think you know how to do the math. Make sure you can get to this point. But when you do solve this for x should come out to be 2.07 molar. All right. Now, again, you have to plug that in to your table here in order to get the actual values for each of these substances at equilibrium. So we know we're going to have 2.50 minus 2.07 for each of your reactants. So that's going to be 0.43 molar. That will be the concentration here of the H2 and the concentration of the F2. And then when you do the math here for the HF, you have 0.500 plus 2 times the 2.07. And then that comes out to be 4.64 molar. And that would be the concentration here of the HF. Okay, so now you have all the concentrations for each of the substances at equilibrium. All right, so this was another version where you didn't know any of the concentrations at equilibrium, so you had to do the ice table with X, but it was different because none of the initial concentrations were zero. So we had to do Q first. All right, you definitely need to be on the lookout for this. If none of the initial concentrations are zero, you have to do Q first to figure out which way the reaction is going to shift. Since we knew it was going right, we knew that the reactants were going to be used up or negative, and the product was going to form or be positive. All right, so look for chances for you to simplify your work with perfect squares. Otherwise, you might have to do the quadratic for some of these problems.